And it's also one of the things that I find best about Kaggle is that you have an appreciation for the fact that most of your ideas are very bad. Like that just because you think it's a clever idea and you haven't seen someone do it before doesn't mean it's a good idea. And Kaggle's a very nice benchmark for showing you that it's a bad idea. And so just, with deep learning, one of the things that people kind of tend to do all the time is come up with new, complicated, fancy models. And this is sort of the hard reality of most of the models you make, even though they're really clever and really complicated and took you hours to program, don't necessarily give you better results. Or as Mary was just saying, that if you don't have very much data, then random forests, which are really simple, work much better than deep learning. And it's sad because deep learning is really complicated, and once you've spent all this time to learn it, you sort of expect to get a nice big payoff because you get better results, but the reality is that it's just another tool, and that most of the tools you try and most of the things you do don't work very well. So as we saw with sort of balancing out the group, we'd expect that to work better, but it didn't. We now try this threshold volume. So that was sort of our first suggestion of trying to sort of take the bright pixels and look at the volume and use that as a metric. And so here we decided to use 500. And then we can change our calc brightness function from np mean of in-image data to np.sum of in-image data greater than 600. And so what that does is it counts all of the voxels that are greater than 600 on the scan. I don't really know what that means, but it seems to be a reasonable number to pick. So I guess it's the gray. Anything that's gray or brighter gets counted. And so we can now we should probably call this something different. So we can call it gray volume. And hopefully that's not.
I mean, I would say it's a white matter.
White matter volume.
I think so. I mean,
looking at the distribution,
I didn't have the.
It's probably gray matter. The first peak is gray matter. The second peak
is white matter.
Yeah.
So again, it's probably better to look at exactly what you've segmented, make some nice layovers and things.
Yeah. Have a fresh one and look at what you are computing.
Yeah. But that here we see in this white matter volume, there's also a very distinct trend. There's also a fair amount of points that are outliers. But we can now take this white matter volume and basically replace anywhere brightness shows up with white matter volume. And we see that the coefficient is 1. Oh, oops. Sorry, age. So your coefficient should almost never be 1, and it's just 1 here, because we put as the x variable the white matter volume, and the variable that we're trying to predict as the white matter volume. And so, again, this sanity check is quite useful, because when you're copying and pasting, it's very easy for things to go wrong. And now we see that it's minus some massive number, which is what we'd expect. So now we can run it on all the test data. Put it in here. Oops. Again, see that the model fits perfectly. It also gives us age predictions that are wildly outside of what we'd expect. So if we go the minimum age is 492.
Oh, that's quite old.
That's very old. So the minimum age is 492 and the maximum age is 492. That also seems very odd. Mm-hmm. So probably, again, something has gone wrong. Oh, calculate brightness. So we want to make sure we're using the right function. Calculate threshold volume. Now we have more reasonable results, and we see that the youngest is 9 and that the oldest is 102. again, with these classifiers, you can always try to incorporate more information or force the oldest age to be 100 or 95. And now we can change this name to threshold prediction. And so I'll make this notebook public in case you missed any of those lines. Hopefully everything works. And so if you now go back to the page, you should see under kernels, a new one.
Will we have access to that or it disappears in 2 days?
Oh no, the competition's over in 3 days, so the leaderboard stops being updated. But you'll have access to this, I think, forever, or as long as Kaggle has money. How come it doesn't show up? Yeah, Google bought them, so I think they're doing reasonably well. Yeah. So yeah, MRI using threshold volume.
Just copy that one. It doesn't count.
So it is public, and then we go to the output, submit to competition, and then we can see if the threshold, so actually it's quite cool. The threshold idea was slightly better. So we're now at 7. So still not quite at the distribution ID. Maybe 600 was the wrong point, or maybe you need to look at gray volume to white volume ratio, but that you can start playing with those. Ah, so someone's already at 1.7. How'd you get to 1.7? Wow.
I think they like competitions.
I guess so, yeah.
Hey guys, there is no prize, just in case. But that's very good.
But no, 1.7 is quite good.
What did you do? Lucas? Thomas? Come on.
We changed the linear classifier with the random progress.
Okay, so maybe it's not even the intensity distribution. Maybe just the classifier already makes a huge difference. But yeah, so you can keep trying out new ideas and see how you move up or down the range, the ranking list with all of these different approaches. So then we'll have 2 sort of fairly quick slides. So sort of the introduction to texture analysis. So again, we don't have time to go over this. There are whole courses set up on these topics. But that basically the idea with texture analysis is right now we focused on brightness and a simple thresholding for the area. And so those are very simple metrics to use to make a classification. And really what you'd want to be able to do is incorporate much more detailed information about the structure you see inside of the image. And so in medicine, this is often called sort of like radiomics, or in radiology it's called radiomics, where you come up with a bunch of different imaging biomarkers based on patterns you see in the images. And so what we have in this notebook is sort of completely unrelated to the competition. It's just a brief example of what it looks like. And so here we have a bunch of different patterns. These are all fake patterns. They're not patterns we'd actually expect to see in a real image, but that we have all of them in here. And how do we sort of describe them? Because they all have, similar brightness. If you thresholded them and counted the volume, you'd probably have similar volumes. At least all of these would have similar volumes, but they all have very different shapes. And so what you use for this is something called sort of like the gray scale correlation matrix, which we have in this thing. What is it? The name of it? Where basically you look at different correlation patterns inside of the image, and given you're at one point, what's the likelihood the next point has a given value? And so that, it's, in an image with a flat constant background, given that your current point is, at 0, you'd expect all the points around it to be 0. And given an image with like a very noisy background, given you at this point, you have very little information about the other points. There could be a lot of different things that are inside. And that's really the core idea of this. And so what we have is we can show the sort of the co-occurrence matrices for all of these different patterns. So we have the patterns along the top row, and then the matrices that we generate from them as sort of the co-occurrence one, and then the average co-occurrence over the whole thing. So that's the same for all of these patterns, but that we see that this matrix here is very different for each one of these patterns. But for this one, it's all empty in this direction, and for some of those more noisy, different patterns, you have a lot more values here. And that you can make some simplifications from this and get, little curves out of it that you see for this one. You have the distance co-occurrence looks like this, whereas in this one, you have sort of a flat profile for that. But you end up with radial co-occurrences. And so you can tell the difference between this pattern and this pattern by looking at what angles those co-occurrences are most likely to occur at. And so ultimately, there's lots and lots and lots of different possible combinations you can get from all of these metrics. We don't really have time to go into all of them. It's just the idea that you can use these tools. This is the very simple one in scikit image, and apply them to images and sort of show, you can get homogeneity, correlation, ASM, all sort of these other factors from an image and use it to start making classifications with it. And so what we have here is the sort of MRI Radiomics overview, where we use a special package called Radiomics. And so if you're interested in that, it's sort of painful to use, but it's really, really powerful. And it's worth learning if you're dealing with medical images a lot. I think there's actually a Radiomics website that looks a lot more fun. Oh, that's it. So it's used by a lot of very, very successful groups for calculating all kinds of very fancy metrics in tumors and predicting people's outcomes. So a lot of the sort of projects that Jonas had mentioned before, these tools have been very important in actually making those predictions and solving those problems. And so here, we'll just show basically how you use the tool for this problem. So you install it using the sort of pip install Radiomics, and then you have to set up the Radiomics feature extractor, which requires a number of different parameters for how you tweak it. And then you feed every image into it. It's along with sort of the mask for the region that you're interested in. And so this mask for us is just all the values that are non-zero. So after you've done the skull removal, what's left inside the brain. But clearly, if you had segmentations for the different parts of the brain, you would want to handle each one of those regions differently. And that you can run it, and you get this result with 129 columns describing all of these different metrics inside your image. And so you can run it on all scans. That takes 49 minutes to do, so you probably don't have time to do it now. But that you can then get all this data and come up with all of these distributions that you can then use to try to fit a model to get a better result. And so what's interesting about these metrics is when you have metrics that are really not correlated with each other at all. So when you get lots of different interesting distributions, it's a lot easier to use those metrics to actually solve a more complicated problem. The last part, go back for this. Just because deep learning was mentioned so heavily in the last lecture, and kind of how do you even, oh no, that's texture analysis, sorry. MRI age using 3D CNNs. And so how do you even get started with deep learning in these sort of problems? And If you haven't done any machine learning and are not comfortable in Python, I wouldn't really recommend spending much time trying to do deep learning because it doesn't necessarily make a lot of sense to do deep learning if you don't understand arrays and matrices and tensors, but to at least have a feeling for what the tools look like and be able to build a simple model is fairly useful. So here, if you go to the MRI age using 3D CNNs, you can again click fork on that to create your own copy of the notebook. You then get to one of the biggest advantages of Kaggle, where you can just turn this GPU on. So for any of you who've worked in labs where you've had to set up a GPU machine yourself, it's a nightmare to try to get the driver set up correctly in the right version of Linux and CUDA, and then TensorFlow, and then all the other tools you need on top of it. And here, all you have to do is click GPU on, and you get access to it. So, of course, all of your notebooks and data are on Google servers, and they're doing who knows what with it. But it saves you a lot of time and lets you do experiments much quicker. And so you can decide for yourself if that's a trade-off you're willing to do. But I've found that for most of the things I do, it makes a lot of sense to just do things quickly in there. And so everything at the beginning looks exactly the same. So if we go through and run each block, it's the same as we had before. It's only once we've loaded a scan that we sort of take a different path. And so deep learning is a bit different from some of the other techniques we did. And so with the other techniques, we sort of calculated features first and then put the features into a model to try to learn a result. With deep learning, what we do is we take the images themselves, put them in a model, and try to learn the result. And so we haven't really done any featureization. You can include features as well, but we won't go into that. And so here we have a fairly basic model, similar to a lot of the ones that Jonas described before, where you have these convolutional layers, these batch normalization steps, which he didn't really mention, but these kind of serve to regularize the model a bit, so to prevent values from kind of getting too out of whack. Activation layers and max pooling. And so here we have all of the kind of ingredients that he had mentioned before. And the first number for convolutions are sort of the number of filters you try to figure out. The second is what dimensions the filters have. So right now we say they're isotropic, they're 3 by 3 by 3 in every direction, but you could of course try different filters. Activation is this ReLU, like he mentioned as well. We have these max poolings, and then we have dropout, again to help normalize it, so to sort of randomly throw out some of the points, and then fully connected layers at the end to make the prediction. So if you have a vague understanding of that, one of the nice things in tools like Keras is that you can just click summary, and you get sort of a list of what your model is to make sure you built what you thought you did. And then you can do this visualization where you can see what your model looks like, how big everything is going to each layer, and what's coming in and what's going out. And so for models like this, maybe it's not quite as important to have all of that information. But if we go to kind of real world models, is this it? It can get very, very complicated very quickly. And so having ways of checking that you've wired everything together in the right way is very important. And so this is an example of sort of, a dilated convolutional model, but you have lots and lots of different blocks and connections and operations that are bringing this whole model together. And if you look at models, like I think one of the ones he said was ResNext, if I'm not what? So ResNext was the really, really big one. So ResNet's already a fairly big one, but ResNext, there aren't any examples. But if you just use ResNet 152, someone must have it looks like that. So it's a fairly common pattern, but knowing which layers are supposed to be connected to which other layers is quite difficult. B3 is another model that gets quite complicated and messy, and so being able to make these plots and look at them makes it easier to sort of figure out what's going on. For us, we stay with a fairly simple model, but it still can be useful to sort of see what's going. Here we then have sort of this next step that with deep learning models, because you're dealing with GPUs and CPUs, you need data loaders. So you need sort of a code that loads a batch of data. So you don't work with single samples. You also don't work with all the data at the same time. And so here we have a fairly basic function that just reads in for young patients, for old patients, and then combines them together. And so this does that balancing step that we wanted before. You could try turning it off and having it not balance and see if you got different results. And then you have sort of a similar but slightly more complicated pre-processing in order to do this model predict. And so here what we do is we predict the absolutely untrained model and kind of see how well it does. And we see if we haven't trained the model at all, it really doesn't get meaningful predictions, which is what we'd expect. And that's why we bother training it. So now we can run the training loop over 20 epochs. And this will then take a fair amount of time, but because we've turned GPU on, it'll run thousands and thousands of times faster than it would have if we ran it on CPU. So you can try rerunning it with GPU off, and I think it'll take weeks potentially to finish running. And that basically what we see, which is also quite important, sort of the visualization of what's going on while you're training. So this is what the last step looks like. So our prediction versus what the actual age was sort of gets better and better. And that if we look over time, here we show the epoch number, and we see the first up until maybe 15 epochs, so passes through the whole data set. It's a flat-ish curve that it's learning. And so it's just learning the average age. So it's not actually incorporating any image features. It's only at the very end, so sort of 17, 18, 19, that it's actually starting to learn the differences between these two groups and give a reasonable result. And so if you trained it longer, it would probably do a much better job of learning the differences between these groups. You can then apply it to test data and do sort of a histogram to see is it learning still a distribution, and then sort of save the results and submit it to the contest and see how it works. So again, are there questions on that? Or probably you'll have to play? Yeah. Oh, that was not a question. Sorry. Probably you'll have to play around with it a little bit more to get more of a feeling for what's going on, but that you can at least try to compete and try to build different models to solve these problems and see if you can do better than sort of standard regression or random forest for solving a fairly simple age from MRI scan problem. And fairly simple. It's not super trivial, and it's also not a problem you could necessarily solve yourself. I can't look at an MRI scan at all and tell you how old the person is, and that's what the model you're trying to build does. It's not just trying to say young or old, it's actually trying to say the actual age. And if we see the results,
I have one more question.
yeah.
Is it always just playing around with stuff and just trying out different models, or is there any rationale behind it?
No, so there is rationale behind it. So people that just do random stuff tend not to do very well. But the rationale usually comes post hoc. So you build something that works really well, and then you try to figure out why it worked. Because most of the time when you do it forward, in the forward direction, you come up with things that should work really well, that are super clever ideas, that just don't. And so, yeah. Oh, wait, someone's beat me now. So someone's at 1.37? Wow, cool.
It's a Gaussian mixed model.
Really?
Oh, that, I love that. Thank you.
Yeah, I mean, that's great. So, yeah, keep trying, keep playing. I mean, the fact that all the baselines have been beat is a quite cool result. And yeah, if you have your code and want to make it public, I guess you can wait until the competition's over and then let other people see what you did so that you don't have people beating you with exactly the same code. But yeah, no, I mean, there is lots and lots of people that try to explain what models do or understand what models do. And you typically find that, people working at Google that have lots of resources and very, clever backgrounds tend to come up with better models than people who are, medical doctors who've installed TensorFlow yesterday. So there is clearly lots of things that experience and understanding of machine learning basics and understanding of mathematics help you with. But ultimately, the results are kind of what drive the understanding. Because, yeah, it's not completely... I mean, so again, it's a field where there's not necessarily a whole lot of theory that backs up everything that's done. But there's a huge difference between people who are very good and people who are very bad. And so, spending time to understand these things does help you improve your results, and it isn't just random choices. I mean, maybe Gaussian mixture model was a random choice, I don't know. But having some understanding for what the model's trying to predict and how you can get good results and how you can change the problem does help it a lot. And in the same sense, Google engineers aren't necessarily coming up with the best algorithms in every medical case. There's a lot of medical problems that require, you don't have very much data. You have very sort of advanced things that have already been built, and bringing those together is something that someone who's just a computer science expert can't do as well as someone who really understands the domain. So yeah, I guess you can continue playing on that, and we'll switch over to the entrepreneurship part, or
Yeah.
I guess we should do that sooner than later. If we want to be done by...
It's fun, actually.
It's 5, yeah?
How long do you think it will take?
It can take as long as it needs.
Yeah, maybe we can start already.
Yeah.